Welcome to part 2 of the theoretical foundations of data flow analysis. This lecture looks at various theoretical aspects of data flow analysis. For example, what are the conditions under which the DFA algorithm delivers correct results, does it terminate, what exactly is the meaning of a solution, etc., and how far are we from the ideal solution, etc. So, last time we discussed the data flow framework, which consists of a direction, a domain of values which is actually a semi lattice, a meet operator for the lattice and a set of transfer functions. So, we started discussion on the properties of data flow algorithms, especially the iterative variety. The first variety is first property is if the iterative algorithm converges, the result is a solution to the data flow equations. So, this is true because if the equations are not satisfied by the time the loop ends in iteration, at least one of the outsets of the various basic blocks changes, and therefore, we need to iterate once again. So, once all the outsets are stabilized and they do not change again, that would be a solution to the equation. If the framework is monotone, then the solution found is the max fixed point of the data flow equations. So, what is a max fixed point? A max fixed point solution is such that in any other solution, the values of in B and out B are actually less than or equal to, in the lattice theoretic sense, corresponding values of the max fixed point value. That is, there will be more conservative, that is less precise. So, in other words, if there is a reaching definitions problem, you may get a slightly bigger set in a solution which is not the MFP solution. So, that does not mean the MFP solution is the ideal solution. We will actually today discuss what exactly is an ideal solution and so on. So, this property that we stated now can be proved by induction on the and the number of iterations of the algorithm is what we are going to induct upon. If the semi lattice of the framework is monotone and is of finite height, then the algorithm is guaranteed to converge, it terminates definitely with a solution to the data flow equations. So, you see there are many nodes in the control flow graph that we are looking at. So, and we have to actually scan every one of those nodes of the flow graph. So, each flow graph possibly would change the value in each iteration. So, and as we saw just now, the values only decrease. Okay. So, from the top the values go towards the bottom, which is the most conservative part. So, that is why the maximum number of iterations in the worst case would be the height of the lattice, that is the maximum number of changes possible to the values multiplied by the number of nodes in the flow graph. This may not happen in practice. Why? Well, in practice the number of iterations is actually 2 plus the depth of the flow graph. We have seen this in one of the previous lectures. So, what exactly do we mean by the ideal data flow solution? So, we try to find an ideal solution by the following method. We find all possible execution paths from the start node to the beginning of the basic block. Let us say we are looking for in values of the basic block. Then, assuming forward flow, we compute the data flow value at the end of each path, that is at the in point of the basic block. So, for every one of these paths, we apply composition of the various transfer functions for the basic blocks involved, and we get so many values. So, we apply the meet operator to these values to find the greatest lower bound or the GLB of these. So, since we have considered a very possible execution, no other execution of the program can produce a smaller value than than what we just now computed. So, this ideal solution would be meet of f p with an initial value v in it over all the possible execution paths from the start node to the beginning of B. So, answers greater than, that is in the sense of the partial order less than or equal to than ideal are incorrect. So, we would have left out some of the execution paths. Any value smaller, that is towards the bottommost point of the lattice, okay, smaller than or equal to the ideal value is conservative, that is safe. So, we would have possibly included some infeasible paths also, that is a condition possibly cannot be executed, but we have taken that branch and considered the path along that part as well. But the solution is safe. In other words, the application will not deliver incorrect results if we use this approximation. Closer the value is to ideal, more precise it is. So, this is the exact solution. This is not achievable in practice simply because you just cannot find all the execution paths of a program. This is an undecidable problem. So, we try to approximate this by including all paths in the flow graph itself. So, this is a graph theoretic path that we are talking about, not an execution path. So, this is called as the meet over all paths solution, MOP, and here we again take f p of v in it, but p is a path from start node to B. So, we are considering all the graph theoretic paths from the start node to the beginning of the basic block B and not the execution paths. So, because we include the graph theoretic paths, some of them may not be executable, some of these paths may never be executed in any execution of the program, and therefore, MOP solution tends to be a little more conservative than the ideal solution. That is why MOP B is less than or equal to ideal B, since we consider a superset of the execution paths. But even this is a bit hard. Finding all the paths in a flow graph may still be impossible. So, what happens if it has a cycle? Then there are infinite number of paths in the graph theoretic sense as well. So, you really cannot enumerate all the paths and do what we wanted. The iterative algorithm does not even try this. So, it visits all basic blocks, not necessarily in execution order. It applies the meet operator at each join point in the flow graph. Okay. So, it does not try enumerating the path and then apply the meet operator for paths, either the graph theoretic paths or the actual execution paths. It just applies it at every join point in the flow graph. The solution obtained is the maximum fixed point solution. So, this is called the MFP solution that we discussed a little while ago. The iterative algorithm delivers this. So, if the framework is distributive, then the MOP and MFP solutions will be identical. So, we will see that the constant propagation framework is not distributive, and therefore, these two solutions do not become the same for that particular framework. So, distributive property is very important. For the reaching definitions problem, the framework is indeed distributive. So, the meet over all paths and the maximum fixed point solutions will be identical. We can do very little about the ideal solution anyway. The best we can do is MOP. So, and here we know that if it is distributive, then MOP and MFP are identical. So, and therefore, we should be happy with this result. So, otherwise if we have just monotonicity like in the constant propagation framework and distributivity is false, then MFP is smaller than the MOP solution and MOP is of course smaller than the ideal solution. So, but whatever we get from the iterative algorithm is still safe. It may be conservative, but it is definitely safe. So, let us show that the MFP solution is indeed smaller than the MOP rather is more conservative than the MOP solution. So, this is the flow graph that we will consider. So, in several examples from now on, start B 1, B 2, B 3, B 4. So, there is a join point at B 3 from B 1 and B 2. So, there are two paths from start to B 4. So, that is easy to see, right, start B 1, B 3, B 4 and start B 2, B 3, B 4. So, now how do you compute the MOP over this flow graph? Very easy. Consider the transfer functions along this path, consider the transfer functions along this path as well, compose these transfer functions separately, compose these transfer functions separately, then apply the join meet operator. So, MOP of B 4 is F B 3 dot F B 1. So, this is the first path, F B 3 dot F B 2, this is the second part, second path. Then we take the meet over these two, and of course, the initial value of the entire data flow problem is V in it. So, this is our MOP solution. So, in the iterative algorithm, we get the MFP solution. So, to do that we must choose some order to visit the nodes of the flow graph. Let us say we assume start B 1, B 2, B 3, B 4. So, that is start B 1, B 2, B 3 and B 4. Okay. So, we do this and then the join point and then B 4. So, in of B 4 would be, so you do F B 1 of V init, you do F B 2 of V init. Now, we have a join point here. So, we apply the meet operator on these two, then do the F B 3. So, this is the in value for basic block B 4. So, observe that this value MOP, which is F B 3 dot F B 1 meet F B 3 dot F B 2 applied to V init, and this solution, that is F B 3 of F B 1 V init meet F B 2 V init, is these two are different, they are not identical, and these two will have equal value only if the framework is distributive. So, if the transfer functions over the lattice are distributive, they satisfy the distributive property, then this and this will be identical, they will have deliver the same value. So, with just monotonicity in of B 4, this value will always be less than or equal to the MOP of B 4. So, this property is well known, and this shows that the maximum fixed point value will always be less than or equal to the meet over all paths value. Let us move on to the constant propagation framework. So, what is the constant propagation problem? The constant propagation problem is to propagate the constant values of variables down in the flow graph. So, whenever there is a constant value assigned to a variable and it does not change, we might whenever the variable is used, we might as well use the constant value, something like that copy propagation applied to constants. So, and whenever there is an expression involving constants, we also evaluate that expression, and the compiler can do this. There is no need to wait for the runtime system to do this. So, and we can now go on using the evaluated value of the expression, constant expression, and do constant propagation further. So, what is the lattice for the constant propagation framework? Let us first consider a single variable. So, here is the constant propagation framework of a single variable. So, you have a top, you have a bottom, and then the constant values. The top says the variable is undefined, the bottom says it is definitely not a constant, and in between the variable can take any of these values, they are incomparable. So, in fact, the combination or evaluation of expressions is defined over and above this lattice, okay, as a transfer function and not as a part of the lattice as such. So, this is the abstraction we are going to look at. This entire middle will be termed as C, a constant. Okay. This top is another abstract value, bottom is one more abstract value. So, we have 3 abstract values for the constant propagation framework. One is the top or undef, then the constant, infinite number of values, and then the bottom, which is not a constant. So, here I should point out that this lattice is indeed infinite. You know, the number of values possible for the constants is definitely infinite, not necessarily in the practical way, but in theoretical way. But the height of the lattice is finite, you know, this is just 2. We also need to understand what exactly is the product of 2 lattices, because the constant propagation framework requires a product of lattices. So, let us take very simple lattices, 2 of them, top 0 bottom, top 1 bottom. Okay. So, nothing else, and we want to do a cross product of these 2 lattices. So, we are going to consider you know, all possible pairs of values, of course, from one to the other, like in a cross product. So, top 1, top bottom, you know, 0 top, 0 1, 0 bottom, bottom top, bottom 1, bottom bottom. So, all these values are here. Okay. Now, when can we say that this value is smaller than this value or this value is smaller than this value? So, in general, we can say that A comma B. Okay. So, this is a pair in the product lattice, C comma D is another pair in the product lattice. So, A comma B is less than or equal to C comma D if and only if the first 2 components are less than or equal to A less than or equal to C, and the second 2 components are again related by less than or equal to B less than or equal to D. So, first component belongs to the first lattice, second component belongs to the second lattice here, and the number of elements in the lattice will be number of elements in S 1 multiplied by the number of elements in the other one. So, 3 into 3, 9 elements here. So, let us verify the inequality in this. So, it is built upon the inequality from this single lattice. So, here you know, 0 less than or equal to top, bottom less than or equal to 0. So, let us take the 0 bottom and 0 1. So, 0 less than or equal to 0 is no problem, and bottom less than or equal to 1 is also no problem. So, this is the way we obviously, for example, you know, we cannot have any connection between top comma bottom and 0 comma top, simply because top is not less than or equal to 0. Okay. So, even though bottom is less than or equal to top, top is not less than or equal to 0, you can see that. And this does not show any transitive relations as usual in the case of a lattice diagram. So, it shows only immediate relationships, and transitivity is to be inferred from the relationships and from the diagram. So, data flow values in the reaching definitions framework can also be considered as values in a product of lattices of definitions. So, we had considered you know, the reaching definitions lattice in which the subsets of the definitions actually are the elements of the lattice. Another way of looking at the problem, you have one lattice for each definition with phi as top and D as the only other element, no other bottom. So, a 2 element lattice. Now, take a product of the lattices of each definition. If there are 10 definitions, then you have a 10-fold product. Okay. So, finally, you will have a product lattice for all the data flow for all the reaching definitions, rather all the definitions in the program, and you can use exactly the same type of argument that we gave here to construct that lattice, and finally, argue about the max fixed point solution and so on and so forth. So, observe that the number of elements is going to be the same. Okay. So, whether we use the product lattice or the subsets of all sets of n elements, it will have exactly the same number of elements. Okay. So, if there are n definitions, each one has 2 elements. So, 2 into 2 into n times is 2 to the power n anyway. So, we still have the same number of elements in the reaching definition lattice considered as a product as well. So, it is possible to consider many others also as product of lattices. The lattice of the data values in the constant propagation framework is the product of semi lattices of the variables, one for each variable, exactly like in the RD scheme that I mentioned now. So, we already saw this in the product lattice A1 B1 is less than or equal to A2 B2 if and only if A1 is less than A2 and B1 is less than B2 in the appropriate lattices. Now, we associate a map with each variable. Okay. So, the map actually gives us the abstract value as in the lattice. I showed you the abstract value in this case, the bottom and then this constant value, or rather the top constant value or the bottom. So, MV is the abstract value as in the lattice of the variable V in the map. So, if variable V is undefined, then MV gives us undef or top. If the variable value is a constant, then it gives you the actual constant value, and if the variable value is not at all a constant, certainly not a constant, then it gives us the bottom or NSC value. So, this is what the MV map for each variable gives us. Each element in the product lattice is a similar but larger map. So, now this map for the product lattice is defined for all variables. Okay. So, again the product lattice would also have a top, bottom and the middle, right, and MV is the abstract value of the variable. So, therefore, in the product lattice, if you are going to have m less than or equal to m prime, then for all variables V, we should have MV less than or equal to m prime V. So, that is what we need to have. So, you have to have this map tells you, okay, take MV, if it is top or bottom, it is trivially satisfied, but if it is somewhere in the middle, then MV must be less than or equal to m prime V, otherwise we do not have any connection between these values. Or in the meet sense, m meet m prime is m double prime if m double prime V is MV meet m prime V for all variables V. So, here it was just for that variable, and here we have for m was for the single variable, but here MV must be less than or equal to m prime V for all variables. So, it is the bigger map here is defined for all variables, and that is why we are justified in saying MV less than or equal to m prime V. So, let us look at the transfer functions. So far we looked at the meet operator in the constant propagation framework. Okay. So, this is the meet operator definition m meet m prime. So, again remember we have a product lattice of the individual variables. Okay. So, and now let us look at the transfer functions for the constant propagation framework. So, assume that you have one statement per basic block. So, transfer functions for basic blocks containing many statements may be obtained by composition. This is a very simple thing which we have already seen. So, MV is the abstract value of the variable in a map M. So, this is the other assumption. The set F of the framework contains transfer functions which accept maps and produce maps as outputs. So, the transfer functions here they take a map and give you another map. Okay. So, that is the way they are, because the elements of the product lattice are maps. So, the transfer functions also must work on maps. So, F contains an identity map, of course, this is a requirement of the framework itself, and map for the start block is m naught v equal to undef for all variables v. So, this is reasonable because nothing is really defined before the program begins. So, let us say f s is the transfer function of the statement yes. Okay. So, let us see how to define f s. So, m prime is f s applied on m. Okay. So, it takes a map and gives you another map. So, how is f s defined? So, if s is not an assignment, then f s is an identity function. So, very simple. So, it is not an assignment at all, then f s is just a simple identity function. If s is an assignment to a variable x, then m prime v is equal to m v for all v not equal to x, provided one of the following conditions also holds. So, what are the various possibilities? Now, we are looking at assignments. RHS of s is a constant. So, we have x equal to c. Now, therefore, we must modify the map, okay, and then say m prime x now becomes c, it is a constant. For this variable, the map will return constant value c, whatever is the constant value. If the RHS is an expression y plus z, so what is the possible? Then you have three cases possible. So, it is either m y plus m z if both m y and m z are constants. So, apply m y, you may get y is a variable, z is a variable. So, m y will give you some value, m z will give you some other value. If these two are constants, then you just add the two constant values, and that is what happens to be the m prime x. So, the map m prime for a x will return that particular constant value from now on. So, this is constant folding. So, if either m y or m z is not a constant value already proved, then m prime x will also become NAC. So, one of them is not a constant, you cannot have y plus z as a constant anyway. In all other cases, it is undef. So, this is the map for the variable x in the new m prime. For all other variables, the map remains the same as before, whatever it was, the value is retained, but for x, the map has now changed. If the RHS is any other expression, then m prime x is NAC. So, this is just covers all other possibilities which we have not been intelligent enough to think of. So, this is regarding the transfer function for the framework. Now, let us start looking at the properties of the transfer function. This these transfer functions actually satisfy the monotonicity property. So, here is the single lattice, rather a lattice for a single variable. Now, let us consider m y, m z and m prime x the way we have just now defined it. M y let us say is undef, then if m z is ndef, m prime x is also undef. So, and if m z is c, a constant, m prime x is still undef because m y is undef, but observe that if one of them is NAC, m z is NAC not a constant, then m prime x becomes not a constant. So, similarly, when m y is a constant, if m z is undef, we remain at ndef. If m z is a constant, then we have the value C 1 plus C 2, and if m z is NAC, then we have NAC. So, for NAC, it does not matter what, we remain at NAC. This is the definition we have just now provided. What should we observe here? It must be noted that the transfer function always produces a lower or same level value in the CP lattice whenever there is a change in inputs. So, let us say one of the values is undef, okay, and the other value changes from undef to C2 to NAC. Let us see how M prime x changes. It was undef, that is at this point, then it was still for C2 it was still at undef, and for NAC it moved down all the way to NAC. So, it went from the top to the bottom as the input Z changed from undef to NAC. When it was My is C1, it starts with undef, then it goes to C1 plus C2, which is again a constant value, and then it goes to NAC. So, with NAC it always remains at NAC, M prime x always remains at NAC. In other words, whenever we have changed the input, the change in M prime x has always been from the top to the bottom. It has never changed from bottom to the top. Okay, it is not as if it was a constant and then it became undef, or it was not a constant and then became constant. This has never happened, and because of this, and it has not gone up and then come down, etcetera, etcetera. It has always travelled from the top towards the bottom. So, this is precisely what we require for monotonicity. Whenever there is a change in input in one direction, the change in the output should also be in the same direction, right. So, that is something that we want. So, this is satisfied, and therefore, the CP framework is monotone. We are also going to prove that the CP framework is not distributive. So, this is a very important thing to show, because probably this is one of the most famous examples which shows that distributivity is important. For our problems such as reaching definitions and so on, the frameworks are indeed distributive. So, there is no problem about that. Okay. We have seen this in the last lecture. So, the implication is, if since the CP framework fails to be distributive and it is only monotone, our MFP solution will not be as good as the MOP solution, it will be slightly inferior. What exactly do we mean by this? So, this example shows that. We have x equal to 2, y equal to 3, and x equal to 3 and y equal to 2. Here we have z equal to x plus y. So, if you add up the values of x plus y at this point, we know that both sides give you exactly 5. So, 2 plus 3 is 5, 3 plus 2 is also 5. So, the value of z, irrespective of the path taken either through B1 or through B2, during execution is actually going to be 5. But the problem is, our data flow analysis cannot determine this, because the value of x here and the value of x here are different, x equal to 2 and x equal to 3. So, the value of x at this point is not a constant, it is either 2 or 3, but it is not the same, it is not a single value. The same is true for y. Y is 3 or 2, it is not a constant at this point. So, therefore, we deem that z is also not a constant. So, how do we show this formally? So, let us look at F1, F2, F3 as transfer functions of the 3 basic blocks B1, B2, B3. So, here is M, it is either Mx, My and Mz, and then M naught. So, this is the initial map, it is undef for all variables. So, you apply F1 M naught. So, what we want to show is F3 of you apply the meet operation at the join point, okay, and not after taking the path, that is what we mean. So, F1 M naught meet F2 M naughts, okay, and then F3. So, this is the MFP part, MFP way, whereas F3 of F1 M naught meet F3 of F2 M naught. So, this is the MOP way. So, let us evaluate for this example these functions, transfer functions, and see what happens. So, apply f1 of m naught, m of x is 2, m of y is 3 and m z is still undef, because we just want to apply for x and y. See, remember here we have only x and y, we do not have z. Similarly, for f2 m naught, again we do not have z here. Okay. So, we get x as 3 and y as 2 and this remains as undef. Now, take that meet. So, f z remains undef, but 2 and 3 give you not a constant, 3 and 2 also give you not a constant. So, because they are not equal, it always gives you the GLB as not a constant. We go downwards. Then apply f3. Well, the damage is already done. You already have an NAC. So, applying any transfer function to NAC will not produce anything but NAC. So, Z now gets NAC from our definition. So, now on F1 so now this is the MFP part of it. Now, let us do the MOP part. Take F1 m naught and then apply F3 on it. Okay. So, we get 5, see this. So, this is Z, x and y do not change, only this. So, we are taking one path, calculate Z. So, we get 5. Take the other path and calculate Z. So, along this path also Z is a constant. So, we get 5. Then take the meet of these two 5s, you get 5 itself. For these two, of course, it is NAC. So, the MOP solution gave us the value 5, a constant for Z, constant value for Z, whereas the MFP solution gave us NAC, not a constant as the solution. So, this shows that the two values are different and therefore, the constant propagation framework is indeed non-distributive. So, this is the end of this particular lecture on theoretical foundations. So, now we will continue this the next lecture on partial redundancy elimination. So, welcome to the lecture on partial redundancy elimination. So, this is a very important optimization and therefore, a complete lecture is being devoted to this particular optimization. We saw an example of what exactly is PRE in the lecture on introduction to optimizations. So, I am producing the same example here to recapitulate what the transformation is. So, we have a very small flow graph in which this basic block has x equal to a plus b, and then the basic block number 4 also has y equal to a plus b, but the basic block number 2 and basic block number 3 do not have any definitions, rather evaluations of a plus b. So, what has happened is this particular expression, if we follow this path, will be computed twice, whereas if we follow this particular path, it is being computed once. So, can we eliminate computing this particular expression twice? So, we can do so. So, how? We introduce the computation of a plus b on this particular path, and now this a plus b is available along this path and also this path. So, we have simply applied global common subexpression elimination, h equal to a plus b, x equal to h equal to a plus b and y equal to h. So, the basic idea is, if then expression is available along one or more path, but not along all paths, then it is said to be partially available. So, such partially available expressions are turned into fully available expressions by introducing some extra computations, and then we apply GCSE and eliminate the common sub expression. So, now you can observe that a plus b is computed exactly once along this path and also along this path. The disadvantage is that you have introduced extra code. So, there is a bit of code blow up, but the advantage of applying partial redundancy elimination overwhelms the bad effects, and therefore, we always go ahead with PRE in a very standard compiler. So, let us begin with some definitions. So, what is a partially redundant computation? A computation which is performed twice, okay, or maybe more number of times in a certain path. So, this is a partially redundant computation. So, what is partial redundancy elimination? It involves insertions and deletions of computations to ensure that no partially redundant computations exist. So, I just showed you the example of this now. An important aspect of PRE algorithm that we have is safety. So, we should not introduce any computation of new values on any path in the program. So, if for example, in this path suppose there was no computation of a plus b along some other path, let us say this, we are not supposed to introduce a new computation along this path. Okay. So, if it has one, fine, if it does not have one, then we should not introduce it. So, that is the basic idea. The number of times it is evaluated is immaterial, here it is 2 and it is 1, that is okay, but 0 and more than 0 really matter. So, safety is a very important feature of our algorithm. We do not want to introduce computations of new values on any path in the program. Why? If we do this, maybe the semantics of the program can be retained by the compiler, there is no problem about that, but when we run the program, it may lead to some runtime errors because of the limitations of CPUs on the overflow of values and underflow of values and things of that kind. So, we do not want any such exceptional situations to occur by introducing extra computations. There has been plenty of previous work. One of the seminal research papers is that of Morel and Renvaux. This was a bidirectional data flow analysis. So, in other words, we have seen forward and backward analyses, both these are involved in the algorithm. So, then it becomes a bidirectional data flow analysis, and therefore, the problem is complicated. It does not eliminate all the partially redundant computations, some of them still remain, and redundant code motion without gain happens. So, the code gets moved, but there is no gain at all. Dhamdare and others improved this algorithm, but then the optimal version was delivered by Knoop and Steffen. They transformed the problem into unidirectional data flow analysis problem. So, there was no bidirectional analysis required, no redundant code motion happened, computationally it was optimal, nothing better could be done, but it needs some blocks and edges to be split right in the beginning, and this is a disadvantage. So, it is somewhat unintuitive and very complex to understand. The highlights of our algorithm are it is simple, intuitive, and it has the same 4 unidirectional flows as in the case of Steffen's algorithm. Computationally and lifetime optimal, again as in the case of Knoop and Steffen's algorithm. And here is the basic advantage, no edge splitting in the beginning, it is needed only at the time of insertion of the computation, that is at the end of the algorithm itself. The second advantage, it yields points of insertion and replacement directly. So, there is no need to compute this separately, this is a part of the algorithm. It introduces the notions of safe partial availability and safe partial anticipability, which did not exist in the previous works. So, what we basically do is a very safe partially redundant computation. We have not yet defined this term. It offers scope for redundancy elimination. So, we turn a very safe partially redundant computation at a point to a totally redundant computation by introducing a new computation at appropriate points by breaking certain edges. The computation of any expression that is totally redundant can now be replaced by a copy rule. So, this is as in the case of global common sub expression elimination, and after the transformation no expression is recomputed at a point if its value is available. So, from the previous computations. So, this is something all these are highlights of our algorithm. So, what are the properties that we require at a point? So, these are the basic things that we require. We already know available expression data flow analysis. So, availability of expressions. So, in all our discussion on PRE, we always refer to properties of expressions. So, all the properties are defined with respect to individual expressions. For each expression there is going to be a set of properties. So, for example, availability, partial availability, anticipability, partial anticipability, safety, etc., etc. So, how do you define the availability of an expression? It is computed along all, the expression is computed along all paths reaching P from the start node with no changes to operands. So, this is availability, it is as usual available at a point implies this anyway. The basic difference here is we are going to have a bit vector which shows availability of various expressions in various basic blocks. Rather, for a single expression in various basic blocks we are going to have availability shown as a bit vector. Okay. So, rather than one bit for each expression there is going to be one bit for each basic block and a bit vector for each expression. Partial availability means computed along at least one path to the point P. So, we have seen an example of this already, we will see more very soon. So, here is an example. So, take this figure A. So, the figure A and B, A plus B is partially available at entry to 4. So, take 4 here. So, entry to 4, we suppose we traverse this path, A plus B is computed here, therefore, it is available, but if we follow this path, A plus B is not computed along this path and it is not available. So, we say A plus B is partially available at this point. The same is true here, if we follow this path, A plus B is available, but if we follow this path, it is not, so it is partially available. Anticipability, computed along all paths starting from P to the end node with no changes to operands. So, there is a computation of the expression coming. Okay. So, from P to the end node, that is anticipability. Partial anticipability is computed along at least one path from P. So, partial availability was computed along at least one path to P, and partial anticipability is computed along at least one path from P to the end node. So, in figure A plus B is partially anticipable at the exit of 1. So, at the exit of 1 here, why is it partially anticipable? If we follow this path, A plus B is indeed computed. So, it is anticipable. If we follow this path, A plus B is not computed, therefore, it is not anticipable. So, in total from here to this at this point we say partially anticipable. Figure B, A plus B is anticipable at the exit of 1. So, at this point we have only one path to take to the end node. So, y equal to A plus B computes A plus B, and therefore, A plus B is anticipable at this point. It is also anticipable at this point and so on. Similarly, at this point again A plus B at the exit of 2, A plus B is indeed partially anticipable. Okay. And if you take the entry to 1, A plus B is anticipable because A plus B is directly computed at this point. It does not matter which path we take. So, what is safety? So, it is actually defined as either available or anticipable. So, in other words, the expression value should arrive from the top or the expression should be computed later. So, one of these must happen. So, what it indicates is there is going to be a computation of the expression and on a path, if at on a path passing through a point, if that point is safe. So, that is why safe points are very important for us, that ensures us that no new computations will be introduced. Safe partial availability is all points on the path of availability from the last computation of the expression to P are safe. So, in other words, we are looking at the last computation of the expression and then the point P. From that last computation to P, the points must be safe. So, here for example, in figure B, A plus B is safe partially available at entry to 4. So, here is the entry to 4. Here is the last computation of A plus B. So, we are looking at this path. The dark circle implies that all these points are safe. What does safety mean? It is either available or anticipable. So, here at this point it is available because A plus B is computed right here. At this point availability is not true because A plus B is not available from this path, but it is anticipable. So, anticipability is true and therefore, the point is safe. This is also safe because anticipability is true even though availability is not true, and this point is also safe because anticipability is true. So, all these points are safe from the last computation of A plus B to this point. Okay. Therefore, the this particular expression is safe partially available at entry to 4. What is safe partial anticipability? All points on the path of anticipability from P to the first computation of the expression are safe. So, A plus B is safe partially anticipable at entry to 3. So, look at entry to 3. So, these are the various points which are all safe. Why is this point safe? Because of availability. Again this path the expression A plus B is available, at this path at this point expression A plus B is available, and so on and so forth. So, at entry to 3 we have availability true even though anticipability is not true. So, this is a safe point and anticipability is partial. Okay. So, from here to here it is anticipable, but along this path it is not anticipable. So, partially anticipable, but safe. So, safe partially anticipable. And safe partially redundant computation, it says locally anticipable and safe partially available at the entry of the node. So, let us understand this. So, here say not safe partially available at entry to 4. So, this is an example to show that. So, we will discuss this particular example in detail in the next lecture with more explanation. Thank you.